Hello everyone. Imagine you're floating far from any star, where space looks empty but never truly is. In that quiet darkness, there are places where gravity doesn't merely pull, it rewrites the rules of escape. Places where the future has fewer options than the past. Those places are black holes. Black holes are famous for a single dramatic line. Not even light can escape. That line is true, but it's also a little misleading because it makes black holes sound like cosmic vacuum cleaners that suck everything in. In reality, from far away, a black hole's gravity behaves like the gravity of any object with the same mass. If you replace the sun with a black hole of exactly the same mass, Earth would continue orbiting almost the same way it does now. We would freeze and die because the sunlight would be gone, but we wouldn't be pulled in. The danger of a black hole is not that it has a special kind of gravity. The danger is how concentrated that mass is, and what happens when you get too close. So what is a black hole, really? It is not a hole in space like a tunnel bored through the universe. It is a region of space-time where gravity is so strong that there is a boundary you can cross beyond which outward no longer leads outward. That boundary is called the event horizon. The event horizon is not a solid surface. It's not a wall. It is a point of no return, defined by the geometry of space-time itself. To understand why that matters, it helps to think in terms of escape. On Earth, you can throw a ball upward and it comes back down because Earth's gravity wins. Throw it faster and it goes higher. Throw it fast enough, about 11.2 kilometers per second, and it won't come back. That speed is Earth's escape velocity. Now imagine a body so compact that the escape velocity at its surface is the speed of light. Light can't go faster than light, so light can't escape. That's the basic intuition behind a black hole, even though the real story is deeper and stranger. Because in Einstein's picture, gravity is not just a force, it is the shape of space-time. Einstein's general relativity says mass and energy tell space-time how to curve, and space-time tells matter and light how to move. A planet follows a curved path not because an invisible force yanks it like a rope, but because it is moving through curved space-time. Light also follows those curves. Near a black hole, the curvature becomes so extreme that all possible paths that still point toward the future tilt inward. You can fire rockets, shine flashlights, scream into the void. None of it changes the fact that outside is no longer a direction you can reach once you are past the horizon. That raises a natural question. If the horizon isn't a solid surface, what would it feel like to cross it? The unsettling answer is that, in many cases, you might not feel anything special at the exact moment. If the black hole is very large, the tidal forces at the horizon can be relatively gentle. Tidal forces are the stretching and squeezing caused by gravity being stronger on one side of you than the other. Near a small black hole, those tidal forces can be lethal far before you reach the horizon. Near a supermassive black hole, the horizon is so large that the change in gravity across your body at that boundary can be surprisingly modest. The universe doesn't always put a dramatic sound effect where our intuition expects one, but you would notice something else: time. General relativity predicts that time flows differently in different gravitational fields. Clocks deeper in a gravitational well tick more slowly compared to clocks far away. This isn't science fiction. We measure it with satellites and precision clocks. Near a black hole, this effect becomes extreme. If someone watches you fall toward the horizon from far away, they will see your motion slow down. The light you send outward will be increasingly redshifted, stretched to longer wavelengths, until it becomes too faint and too slow to detect. From their perspective, you never quite cross. You fade, you dim, you freeze near the edge. From your perspective, your own clock behaves normally. You cross the horizon in a finite amount of time. This is not a contradiction. It's a feature of relativity. Different observers slice space-time into now in different ways. The horizon is not a place where time stops for you. It is a place where the global structure of space-time changes so that messages cannot return to the outside universe. That is the basic picture. Now, let's build it into a story. Where black holes come from, what we observe, what we don't yet know, and why these objects sit at the center of some of the deepest questions in physics. The most familiar black holes form when massive stars die. A star is a balance between inward gravity and outward pressure. For most of its life, a star resists collapse because nuclear fusion in its core releases energy, heating the gas and creating pressure. Fusion is like a furnace that pushes back against gravity, but no furnace runs forever. When a very massive star exhausts its nuclear fuel, the outward support weakens. The core collapses. If the collapsing core is not too massive, it can compress into an incredibly dense object called a neutron star, where protons and electrons are crushed together into neutrons, and the star becomes a city-sized sphere. With about the mass of the Sunday neutron stars are already extreme. A teaspoon of neutron star material would weigh billions of tons. Yet even neutron stars have a limit. If the mass is too high, even neutron degeneracy pressure, the quantum pressure that resists, squeezing neutrons into the same state, cannot halt the collapse. Gravity wins completely. The core continues to fall inward, and a black hole is born. This is not always a clean, symmetric process. In many cases, the collapsing star triggers a supernova explosion. The outer layers are blasted outward, and the core either becomes a neutron star or collapses into a black hole. The details depend on the star's mass, rotation, chemical composition, and the complex physics of neutrinos and shock waves. But the key idea is simple. When you pack enough mass into a small enough volume, space-time curves so strongly that an event horizon forms. These stellar mass black holes typically have masses of a few times the Sun, sometimes tens of times the Sunday. For a long time, we assumed black holes from star collapse would cluster in that range. Then gravitational wave detectors showed us black holes merging with masses of 30, 50, even more solar masses, suggesting a richer population shaped by stellar evolution, metallicity, and earlier generations of stars. Every new detection is like hearing another note in the universe's hidden orchestra. Beyond stellar mass black holes, there are supermassive black holes, monsters with millions to billions of times the Sun's mass, living in the centers of galaxies. Our own Milky Way hosts one, called Sagittarius A*. It is quiet most of the time, which is fortunate for us, but it is unquestionably massive. How do such enormous black holes form? That's still an active area of research, and the answer may involve multiple pathways. One pathway is growth by eating. A black hole can gain mass by accreting gas and dust. Matter spirals inward, forming an accretion disk. Friction, turbulence, and magnetic fields heat the disk to enormous temperatures, causing it to glow across the electromagnetic spectrum. When the black hole is feeding aggressively, the center of the galaxy can outshine the rest of the galaxy. We call these blazing cores active galactic nuclei, and at the extreme end, quasars, objects so luminous they can be seen across the observable universe. But eating alone may not be fast enough to explain supermassive black holes already present in the early universe, when the cosmos was less than 1 billion years old. To get a black hole of 1 billion solar masses so quickly, you may need a head start. That leads to other hypotheses: direct collapse of huge primordial gas clouds into massive black hole seeds, rapid growth under special conditions, or mergers of many black holes and dense star clusters. Nature may be using several strategies at once, depending on environment. Between stellar mass and supermassive black holes lie the intermediate mass black holes, perhaps hundreds to hundreds of thousands of solar masses. For decades, they were the missing link. Evidence has been mounting, especially in dense star clusters and dwarf galaxies, but the population is still being mapped. If intermediate mass black holes are common, they may help explain how supermassive black holes grow. If they are rare, that tells a different story about the early universe and the efficiency of growth. There is also a more speculative category: primordial black holes, hypothesized to form from density fluctuations in the very early universe, not from stars. Depending on their mass, they could have evaporated long ago via Hawking radiation, or might still exist today. Some have wondered whether primordial black holes could contribute to dark matter. Observations constrain this possibility strongly, but it remains a fascinating idea because it connects black holes to cosmology and the birth of structure in the universe. So black holes come in different sizes and origins, but they share a set of defining features, like members of a strange family. The simplest black hole model is non-rotating and uncharged, described by the Schwarzschild solution. Real black holes, however, almost certainly rotate, because everything in the universe rotates. Stars spin, gas clouds swirl. When matter collapses, angular momentum is conserved, so rotation speeds up like an ice skater pulling in their arms. A rotating black hole is described by the Kerr solution, and rotation changes the space-time around it dramatically. One key region around a rotating black hole is the ergosphere. In the ergosphere, space-time is dragged along by the black hole's rotation, a phenomenon called frame dragging. It becomes impossible to remain stationary relative to distant stars. You are compelled to co-rotate, at least somewhat. This region allows exotic processes. In principle, you can extract energy from a rotating black hole, like tapping a cosmic flywheel. This is not just a theoretical parlor trick. It may be related to how some black holes power enormous jets. Now, about those jets. If black holes don't let light escape, how can they be associated with some of the brightest phenomena in the universe? The trick is that the brightness comes not from inside the horizon, but from the environment just outside it. Matter falling toward a black hole converts gravitational potential energy into heat and motion. In an accretion disk, particles collide and magnetic fields twist. The disk can reach temperatures so high it emits X-rays. Magnetic fields can channel some material into narrow beams that shoot outward along the rotational axis at near light speed. These jets can extend thousands of light years, punching through interstellar gas and shaping the evolution of the host galaxy. In other words, black holes can be engines. Their power source is gravity and rotation, and their output can regulate star formation by heating or expelling gas. A galaxy is not just a collection of stars. It is an ecosystem of gas, dust, radiation, and gravity. Supermassive black holes can act like a thermostat, sometimes preventing gas from cooling and forming new stars, sometimes triggering bursts of star formation by compressing gas in shocks. The details are complex, but the big picture is clear. Black holes are not merely consumers. They can be cosmic influencers. Now let's talk about a crucial point. We cannot directly see a black hole in the way we see a planet or a star. So how do we know they exist? We infer black holes through their effects. One method is orbital motion. If you find a star orbiting an invisible object, and you can measure the star's orbit, you can infer the mass of the unseen object. In our galaxy's center, astronomers tracked stars moving on tight, fast orbits around an unseen mass concentrated in a very small region. The mass is millions of times that of the Sun, but the region is not much larger than our solar system. No cluster of ordinary stars could be packed that tightly without quickly collapsing or dispersing. The simplest explanation is a supermassive black hole. Another method is X-ray binaries. Sometimes a black hole is in a binary system with a normal star. Gas from the star can be pulled toward the black hole, forming an accretion disk that emits X-rays. By studying the motion of the companion star and the properties of the radiation, astronomers can estimate the mass of the compact object. If the mass exceeds the maximum possible for a neutron star, it is a strong black hole candidate. Then there is gravitational lensing. Mass bends light. A black hole, like any mass, can distort the path of light from objects behind it, creating arcs, multiple images, or magnification. Lensing alone doesn't prove the lens is a black hole, but in combination with other evidence, it can support the picture of a massive compact object. And then there is the modern revolution: gravitational waves. Gravitational waves are ripples in space-time itself. When massive objects accelerate, especially in asymmetric ways, they can radiate energy in the form of these ripples. The strongest sources we can currently detect are mergers of compact objects, black holes and neutron stars. When two black holes orbit each other, they lose energy to gravitational waves, spiral inward, and eventually merge. The final moments release an immense burst of space-time vibrations. Detectors like LIGO and Virgo measure these vibrations as tiny changes in the length of long interferometer arms, changes smaller than a proton. Yet these instruments have captured dozens and then hundreds of events, each one a cosmic collision. The waveforms match the predictions of general relativity with stunning precision. From the waveform, we can infer the masses and spins of the black holes and how far away the event occurred. This is like hearing the universe rather than seeing it. And what we've heard is unmistakable. Black holes exist and they merge. Another landmark achievement is the image of a black hole. Shadow. The Event Horizon Telescope is not a single telescope, but a global network of radio telescopes linked together to form an Earth-sized virtual telescope. With that resolution, we can probe the region around the event horizon of nearby supermassive black holes. The result is not a photograph of the horizon itself, but an image of glowing plasma around it, bent and shaped by extreme gravity. At the center is a dark region, the shadow, corresponding to light paths captured by the black hole. The ring-like structure arises because light can orbit near the black hole before escaping, and because lensing focuses emission into a bright ring. This is not merely visually impressive, it is a test of gravity in the strong field regime. The size and shape of the shadow align with what general relativity predicts for a black hole of that mass and distance. The universe is giving us direct evidence that the no-escape boundary is real, not just a mathematical trick. So we have black holes as astrophysical objects. Now we can ask the deeper questions. What happens inside? What happens to information? And why black holes are where our best theories collide. Inside the event horizon, the roles of space and time effectively change. This is hard to picture without equations, but the intuition is powerful. Outside the horizon, you can choose to move toward or away from the black hole. Inside the horizon, moving toward the center is as unavoidable as moving toward tomorrow. You can slow down, you can twist, you can delay, but you cannot avoid the future. And inside the horizon, the future direction points towards smaller radius. The center becomes less like a location you can avoid and more like an event waiting ahead. Classical general relativity predicts that once inside, you reach a singularity, a point where density and curvature become infinite. Infinite values in physics often signal that the theory is being pushed beyond its domain. Just as classical physics breaks down inside an atom and needs quantum mechanics, general relativity may break down at the singularity and require a theory of quantum gravity. We don't yet have a complete quantum theory of gravity, but we have clues, and black holes are a prime place to hunt for them. One of the biggest clues came from Stephen Hawking. In the 1970 seconds, Hawking showed that black holes are not truly black when quantum effects are included. Quantum field theory predicts that the vacuum is not empty, it seethes with fluctuations. Near the event horizon, these fluctuations can lead to particle creation in a way that allows radiation to escape Hawking radiation. The black hole loses mass over time, effectively evaporating. For a stellar mass black hole, Hawking radiation is unimaginably weak, far below the cosmic microwave background temperature, and evaporation would take vastly longer than the current age of the universe. But conceptually, it is profound. It means black holes have a temperature, they have entropy, they obey laws that resemble thermodynamics. This leads straight into the black hole information paradox. In quantum mechanics, the evolution of a closed system is unitary, which roughly means information is conserved in a very precise sense. If you know the exact quantum state now, the laws allow you to evolve it backward and forward without losing information. But if black holes evaporate via Hawking radiation, and if that radiation is purely thermal random, featureless, then it seems the details of what fell in are lost. A pure state could become a mixed state. Information would be destroyed. That's a problem, because quantum theory does not like information destruction. It breaks the predictive structure of the theory. So where could the information go? Several possibilities have been proposed over the decades. Maybe information is somehow stored at the horizon and encoded in subtle correlations in the Hawking radiation. Maybe the radiation is not truly featureless, and the correlations are the key. Maybe what we think of as inside is not independent from outside in the quantum description. Ideas like holography suggest that information about a volume of space can be encoded on its boundary, like a three-dimensional world described by a two-dimensional surface. In some theoretical frameworks, black holes are the ultimate expression of that principle. There are also radical proposals involving firewalls, hypothetical regions of high-energy particles at the horizon that would destroy anything falling in, contradicting the smooth crossing predicted by general relativity. Firewalls are controversial because they force you to give up either the equivalence principle of relativity or the unitarity of quantum mechanics, or some other cherished assumption. The fact that physicists debate these ideas so intensely tells you how central black holes are to the foundations of physics. They're not just astrophysical objects, they're conceptual stress tests. Now, let's slow down and address some popular myths, because black holes are magnets for misconceptions. Myth 1. Black holes suck everything in. They don't. If you orbit a black hole at a safe distance, you can orbit indefinitely, just as you can orbit a star. The difference is that near the black hole, the stable orbits end closer in, and any small mistake can have more dramatic consequences because of the steep gravitational gradients. But a black hole does not reach out and grab distant objects like a cosmic vacuum cleaner. Most of space is empty. Even in a galaxy's center, the chance of a star directly hitting the black hole is small. The black hole grows mainly by accreting gas that loses angular momentum. not by swallowing stars like snacks, though stellar disruptions do happen. Myth 2. If you fall into a black hole, you are instantly crushed at the horizon. Not necessarily. As mentioned earlier, tidal forces depend on black hole mass and your distance from it. For a small black hole, yes, the tidal forces can be extreme well before the horizon. For a supermassive black hole, the horizon can be crossed without immediate spaghettification, though deeper inside the tidal forces will grow and eventually become fatal. Myth 3. Black holes are portals to other universes. The mathematics of relativity allows exotic solutions like wormholes in certain idealized cases. But real astrophysical black holes formed by collapse are not expected to be traversable wormholes. They likely do not lead to other places you can visit and come back from. The horizon is a one-way boundary. If the universe had a network of traversable shortcuts, it has not left us clear observational evidence yet. It's fun to imagine, but it's not something we can responsibly claim as fact. Myth 4. Black holes violate physics. They don't, they challenge it. Black holes are predicted by general relativity, and we observe phenomena consistent with those predictions. The weirdness is not a sign that the universe is broken. It's a sign that human intuition evolved for throwing rocks, not for navigating curved space-time near the speed of light. Now let's go deeper into the experience of falling toward a black hole, because this is where relativity becomes visceral. Suppose you are in a spaceship far from the black hole, and you start to fall in. At first, nothing seems unusual. The starfield looks normal. Your instruments work. But as you approach, you notice lensing. The black hole bends light, distorting the sky. Stars behind it may appear in strange positions. Multiple images may form, and the background becomes warped. If you are near a bright accretion disk, the scene becomes even more dramatic. The disk may look like a glowing ring because light from the far side is bent around to your view. Some parts of the disk appear brighter due to relativistic beaming. Material moving toward you emits light that is blue-shifted and concentrated in your direction, while material moving away is dimmer and red-shifted. If the black hole is rotating, frame dragging adds another layer. Space-time itself is swirling, affecting the paths of light and matter. There is a region where orbiting becomes unavoidable. As you fall, you may try to send a message to a friend far away. At first, the message arrives normally. Later, your friend receives it increasingly delayed and redshifted. Your voice becomes lower and slower, then fades into silence. You can still talk. Your friend just can't receive it in any meaningful way. This asymmetry is the heart of the horizon. The horizon is not a magical barrier that stops you from moving. It is a barrier that stops information from escaping. If we keep following you inward, classical relativity says you eventually encounter the singularity. But again, we should be humble. We do not know what quantum gravity does there. The singularity may be replaced by something else, a bounce, a quantum region, a new phase of spacetime. Some speculative models suggest the interior could connect to a new region of spacetime. Others suggest it ends in a way that cannot be described by classical geometry. At present, these are ideas, not confirmed realities. What we can do, and what scientists excel at, is measure what happens outside. And what happens outside a black hole is rich, dynamic, and observable. Consider the accretion disk again. Matter doesn't fall straight in unless it has almost no angular momentum. Usually it spirals. As it spirals, it heats up. That heat is radiation. In X-ray binaries, we see rapid variability flickering because the emitting region is small and close to the black hole. The timescales can be milliseconds to seconds. That flickering is like hearing the sizzling of matter as it approaches the edge. We also observe iron emission lines that are broadened and skewed by relativistic effects, giving us information about how fast the disk is moving and how close it extends toward the black hole. The innermost stable circular orbit depends on spin. A rapidly spinning black hole allows stable orbits closer in, changing the disk's behavior. By modeling these spectra and timing signals, astronomers estimate black hole spins and test strong gravity. There are also tidal disruption events, when a star wanders too close to a supermassive black hole. The black hole's tidal forces can rip the star apart, stretching it into a long stream. Some of the material is flung outward, while some falls in, producing a bright flare that can outshine the entire host galaxy for a time. These events are catastrophic on a stellar scale, but they are also scientific gifts. They let us watch black hole feeding episodes in real time. And then there are mergers. When two black holes merge, the final black hole rings like a struck bell, emitting gravitational waves in a pattern called the ring down. The frequencies and damping times depend on the black hole's mass and spin. This is remarkable because it means black holes are simple in a profound way. According to the no-hair idea, in relativity, an isolated black hole can be fully described by just a few parameters: mass, spin, and charge. Charge is expected to be negligible astrophysically, so in practice, mass and spin dominate. Everything else about what formed the black hole, what star collapsed, what matter fell in, doesn't show up in the outside gravitational field in a lasting way. The universe forgets the details, at least classically. That forgetfulness is part of what makes the information paradox so sharp. If the outside only remembers mass and spin, where did the detailed information go? This question has driven enormous progress in theoretical physics, including connections between gravity, quantum entanglement, and the nature of space-time itself. In modern research, some physicists talk about space-time emerging from entanglement patterns, and black holes serve as the laboratory where these ideas are tested mathematically. Now, let's connect black holes to something even bigger: the history of the universe. When the universe was young, it was filled with hot plasma and then cooled into gas, which formed the first stars and galaxies. The earliest stars were likely massive, made of mostly hydrogen and helium, because heavier elements had not yet been forged. Massive stars die quickly and can leave behind black holes. Those early black holes could serve as seeds for growth, possibly helping to form the supermassive black holes we see later. At the same time, black holes and stars are part of the cosmic cycle of elements. Heavy elements like carbon, oxygen, silicon, and iron are forged in stars and distributed through supernovae and mergers. Black holes themselves don't create elements, but the processes that lead to black holes, the life and death of massive stars, the collisions of compact objects, help enrich the interstellar medium. Planets, chemistry, and life depend on that enrichment. In a way, black holes are tangled into the story of our own existence, not by giving us matter, but by participating in the violent events that spread it. Black holes also teach us about extremes of density, temperature, and gravity. They let us test relativity not as an elegant set of equations, but as a description of nature under the harshest conditions. Every time we observe a star orbiting Sagittarius A*, every time we detect an X-ray flare from an accretion disk, every time we hear a gravitational wave chirp, we are checking whether our understanding holds up. So far, Einstein's theory is performing spectacularly well. But physics is not only about confirming theories, it's also about finding the cracks places where a deeper theory is needed. Black holes might be where those cracks will appear. One possible crack involves the nature of horizons. Another involves how quantum information behaves in curved space-time. Another involves what happens at the threshold of collapse. There are objects proposed that mimic black holes, closely exotic compact objects without true horizons, such as gravastars or boson stars. Many of these are speculative, but they are valuable because they force us to ask, what observational signatures would distinguish a true event horizon from a very compact surface? Could we detect echoes in gravitational waves? Could we see differences in how matter behaves near the boundary? These questions turn philosophical uncertainty into testable science. Even the phrase black hole hides subtlety. In relativity, the horizon depends on the global structure of space-time, on the entire future of the universe in a sense. That sounds mind-bending, but it means defining a black hole can be more subtle than drawing a circle around it. Physicists also talk about apparent horizons and trapped surfaces, which are more local and practical. In dynamical situations like mergers, horizons can form and change shape in complex ways. Yet, despite this complexity, the astrophysical signature remains robust, a region where signals can't escape and where matter displays characteristic high-energy behavior. Now, if you're making a video, it can be powerful to ground these ideas with a few thought experiments that feel intuitive. First thought experiment: the sun replaced by a black hole. As mentioned, Earth keeps orbiting. Gravity depends on mass and distance. The difference is that a black hole has no luminous surface. The sky goes dark. This separates the concept of gravity from the concept of light. A black hole is not dangerous because it is magically stronger. It is dangerous because it packs mass into a small region and creates a boundary of no return. Second thought experiment: falling in while sending messages out. Your friend watches your signals slow and redden. You experience normal time. This demonstrates relativity's core lesson. Time is not universal. It depends on motion and gravity. Near black holes, this becomes dramatic. Third thought experiment: tidal forces. If your feet are closer than your head, gravity pulls your feet more strongly. You stretch. If the black hole is small, you stretch violently. If it's large, you might not feel much at the horizon. This shows that how it feels depends on the black hole's size, not just the fact that it's a black hole. These thought experiments don't require equations, but they keep the story accurate. They also help your audience appreciate that black holes are not just scary. They are logical consequences of well-tested physics. Now let's address something your viewers may wonder. If black holes eventually evaporate, could they disappear entirely? In principle, yes. A black hole that is not gaining mass and is isolated in a cold enough universe will lose mass via Hawking radiation and shrink. As it shrinks, it gets hotter and radiates more. The final stage, in some models, could be a burst of high-energy particles. However, for black holes of astrophysical mass, this timescale is so enormous that it's not relevant to the current universe. If you want a number without drowning in it, it's far, far longer than the age of the universe, so long that writing it down feels like a joke the cosmos tells to human patience. That said, the concept matters because it ties black holes to thermodynamics. Black hole entropy is proportional to the area of the event horizon, not the volume. This is strange. It suggests that the information content scales with surface area, which is exactly the kind of clue that leads to holography. It is one of the reasons physicists suspect that space-time might have a deeper, possibly discrete, quantum structure. Now we can zoom out again and see black holes as part of a bigger pattern. Nature has limits and thresholds. There is a threshold where a star becomes a white dwarf and is supported by electron degeneracy pressure. There is a threshold where it becomes a neutron star, supported by neutron degeneracy pressure. And there is a threshold where nothing stops collapse and a black hole forms. These thresholds are like cliff edges in the landscape of physical law. Walk far enough, and the ground changes. Black holes also reveal the interplay between simplicity and complexity. On the outside, a black hole can be described by just mass and spin. On the inside, or in the quantum description, there may be a vast number of microstates accounting for its entropy. So is a black hole simple or complex? Classically, it's the simplest macroscopic object. Quantum mechanically, it may be one of the most information-rich. If you want a poetic way to say it, a black hole is a library that looks like a blank cover from the outside. Let's bring the story to the present day. What are the big open questions? One open question is the detailed growth history of supermassive black holes. How did they form so early? What were the seeds? How did feeding and mergers compete over cosmic time? Upcoming observatories and surveys will map quasars and active galactic nuclei across the universe, helping us reconstruct that timeline. Another open question is the population of intermediate mass black holes. How common are they? Do they hide in globular clusters? Do they live in dwarf galaxies? Gravitational wave detections may reveal them through mergers at higher masses, and electromagnetic observations may find their feeding signatures. Another is the nature of accretion and jet formation. We have models, but the detailed plasma physics in strong gravity and intense magnetic fields is extraordinarily hard. Simulations are improving rapidly. Observations across multiple wavelengths, coordinated in time, are helping constrain those models. And then there is the deepest question: quantum gravity and information. Does the horizon have structure? How does information escape in Hawking radiation, if it does? Is space-time emergent from entanglement? These questions are not only about black holes, they're about the underlying architecture of reality. If your video aims to leave the audience with a sense of wonder without slipping into fantasy, you can end on a note like this. Black holes are not cosmic mistakes or supernatural monsters. They are what happens when the universe takes its own rules seriously and follows them to their logical extreme. They prove that space and time are not rigid stage floors, but flexible, dynamic ingredients of nature. They show that light can be trapped, that time can tilt, that gravity can become geometry so steep the future has only one direction. We used to think the universe was a clockwork of solid objects moving through empty space. Black holes shattered that picture. They replaced it with something stranger and more beautiful. A universe where emptiness has structure, where information has weight, where geometry can ring like a bell, and where the most invisible objects can shape galaxies, light up the sky through their surroundings, and send tremors through the fabric of space-time itself. And perhaps the most humbling part is this: we understand black holes not because we have touched them, but because the universe leaves fingerprints everywhere. In the orbit of a star, in the flicker of X-rays, in the arc of bent light, in the brief chirp of gravitational waves crossing Earth after traveling for billions of years. Black holes don't show us their faces, but they cannot hide their influence. So the next time you look at a calm night sky, remember that some of the darkest places out there are not empty at all. They are full of physics, full of questions, and full of the kind of mystery that doesn't demand belief, only curiosity. Because in the end, a black hole is not just a thing. It's a boundary between what we can observe and what we can only infer. A meeting point of our best theories, and a reminder that the universe is always deeper than the stories we tell about it. That's all for now. Good night.